A fighter jet is not just a fast airplane. It is a flying combat system, engineered to operate at the absolute limits of physics, materials, and human endurance. When a pilot pulls hard on the controls, the aircraft experiences forces that would instantly incapacitate an unprotected human. When afterburner is engaged, fuel is burned at a rate that would empty a car's tank in seconds. And when a fighter jet breaks the sound barrier, air itself changes behavior. The first critical thing to understand is this: a modern fighter jet is intentionally aerodynamically unstable. Unlike commercial aircraft, it is not designed to naturally return to straight and level flight. Without onboard computers, a modern fighter would be almost impossible to control. This instability is not a flaw. It is the source of its extreme maneuverability. A fighter jet must satisfy several opposing requirements at the same time. It must be extremely fast to intercept targets. It must be incredibly agile for close-range air combat. It must carry weapons, fuel, sensors, and electronic systems. And it must remain controllable across an enormous speed range, from slow landing approaches to sustained supersonic flight. If you like similar educational videos, please like, subscribe, and share the video with your friends. This leads to one of the biggest misconceptions. A fighter jet does not fly because of engine power alone. The engine does not lift the aircraft into the air. Lift, maneuvering, and control come from aerodynamics, pressure differences, airflow management, and controlled generation of lift. The engine's role is to provide the energy needed to reach and maintain the required speed. However, fighter jet aerodynamics work very differently from those of civilian aircraft. Wings are shorter, sharply swept, and often combined with additional lifting surfaces. Airflow is deliberately manipulated to create controlled vortices that help maintain lift even at extreme angles of attack. This is why a fighter jet can fly in conditions that would cause a conventional airplane to stall and fall out of the sky. Speed introduces another layer of complexity. As an aircraft approaches the speed of sound, air no longer behaves smoothly. Shock waves form, drag increases dramatically, and control becomes more difficult. Fighter jets must therefore be shaped specifically for transonic and supersonic flight, with airframes designed to manage shock waves and minimize energy loss. And this is only the beginning. In reality, the pilot does not directly control the aircraft at all. Instead, the pilot issues commands to computers that make thousands of corrections per second, constantly adjusting control surfaces and engine behavior to keep the aircraft stable and responsive. To understand why a fighter jet can maneuver in ways that seem almost impossible, you have to abandon the rules of conventional aircraft design. Commercial airplanes are built to be naturally stable. If the pilot releases the controls, the aircraft tends to return to straight and level flight. A fighter jet is designed to do the exact opposite. Modern fighter jets are deliberately aerodynamically unstable. Their center of lift and center of gravity are positioned so that the aircraft constantly wants to change attitude. This instability allows the jet to respond instantly to control inputs, making extreme maneuvers possible. Without continuous correction from onboard computers, the aircraft would quickly become uncontrollable. Stability is sacrificed in exchange for agility. The wings of a fighter jet reflect this philosophy. They are short, sharply swept, and relatively small compared to the aircraft's weight. These wings are not optimized for fuel efficiency or gentle handling at low speeds. Instead, they are optimized for high-speed flight, rapid changes in direction, and survival in extreme aerodynamic conditions. A key concept here is the angle of attack, the angle between the wing and the oncoming airflow. In most aircraft, exceeding a critical angle of attack causes airflow to separate from the wing, leading to a stall and loss of lift. Fighter jets are designed to operate beyond traditional stall limits. Rather than avoiding airflow separation, they use it. At high angles of attack, fighter jets intentionally generate strong aerodynamic vortices along the leading edges of the wings and the fuselage. These swirling flows of air keep energy in the airflow, delaying full separation and maintaining lift even when the aircraft is pitched steeply upward. Lift is no longer produced only by smooth airflow over a wing profile, but by vortex-controlled flow. The fuselage itself also plays a critical role. In a fighter jet, the fuselage is not just a container for fuel, weapons, and the pilot. It is an active lifting surface. At high speeds and extreme angles, the body of the aircraft contributes significantly to total lift. The entire aircraft is designed as a single aerodynamic system, rather than a collection of separate components. Such extreme aerodynamics would be impossible for a human to manage directly. Reaction times are too short, and the aircraft's instability is too severe. This is why all modern fighter jets rely on fly-by-wire control systems. The pilot's inputs are interpreted by computers, which constantly adjust control surfaces to keep the aircraft within controllable limits while still executing the desired maneuver. From the pilot's perspective, the jet feels stable and responsive. From a physics perspective, it is a machine that is constantly on the edge of losing control, saved only by continuous, rapid computer corrections occurring hundreds or thousands of times per second. Aerodynamics alone, however, is not enough. All of this extreme maneuvering, vortex generation, and shockwave management requires vast amounts of energy. Without an engine capable of delivering sustained thrust under extreme conditions, none of this design would be usable. In a fighter jet, the engine is not just a source of propulsion. It is a core part of the aircraft's combat capability, designed to operate where ordinary jet engines simply cannot. A fighter engine must deliver massive thrust, respond instantly to pilot commands, and remain stable across an extreme range of speeds, altitudes, and airflow conditions, including sustained supersonic flight. At its core, a jet engine works on a simple principle. Air is drawn in, compressed, mixed with fuel, ignited, and expelled rearward at very high speed. The reaction force produces thrust. In a fighter jet, however, every step of this process is pushed to its absolute limits. Air may enter the engine at speeds close to or above the speed of sound. Temperatures inside the engine exceed the melting point of many metals, and pressure ratios are extreme. One of the most critical components is the air intake. At high speed, especially in supersonic flight, air cannot simply rush straight into the engine. If it did, the compressor would stall or be destroyed. Fighter jets use carefully shaped intakes that create shock waves to slow the airflow before it reaches the engine. These shock waves reduce the air's speed while increasing its pressure, allowing the engine to function safely. The exact geometry of the intake has a major impact on performance and is the result of intense aerodynamic optimization. Inside the engine, temperatures are so high that conventional materials would fail instantly. Turbine blades are made from single crystal superalloys and often cooled internally by carefully routed airflow. This allows the engine to survive temperatures hotter than molten metal. Without these advanced materials and cooling techniques, modern fighter engines would be impossible. A defining feature of fighter jets is the afterburner. When engaged, additional fuel is injected into the exhaust stream behind the turbine and ignited. This dramatically increases thrust, allowing rapid acceleration, short takeoffs with heavy payloads, and the ability to push through the sound barrier. The cost is enormous fuel consumption. In afterburner, a fighter jet can burn fuel at a rate that limits its use to short periods. Supersonic flight introduces a completely different aerodynamic regime. As the jet approaches Mach 1, drag rises sharply due to shockwave formation. Breaking through this barrier requires a surge of thrust. Some modern fighters are capable of supercruise, meaning they can sustain supersonic flight without using afterburner. This is only possible through a combination of highly efficient engines and aerodynamics optimized to minimize wave drag. In many modern fighters, the engine also contributes directly to maneuverability through thrust vectoring. By slightly redirecting the exhaust flow, the engine can help rotate the aircraft, especially at low speeds or very high angles of attack, where traditional control surfaces lose effectiveness. In these situations, the engine becomes part of the flight control system itself. The engine, then, provides more than speed. It provides control, responsiveness, and survivability in flight regimes where physics becomes unforgiving. Yet even with immense thrust and advanced aerodynamics, the fighter jet would still be unusable without protecting the pilot and managing the aircraft's instability. When a fighter jet reaches its full combat performance, the aircraft itself is no longer the limiting factor. The human body is. During aggressive maneuvers, the pilot experiences extreme G-forces that multiply their effective body weight many times over. Blood is pulled away from the brain, oxygen supply drops, and without protection, loss of consciousness would occur in seconds. For this reason, modern fighter jets are designed around human physiology as much as aerodynamics and propulsion. Pilots wear anti-G suits that automatically inflate under high acceleration, squeezing the legs and abdomen to prevent blood from pooling away from the brain. The cockpit seat is reclined rather than upright, reducing the vertical distance blood must travel. Even with these measures, human tolerance defines a hard operational limit that aircraft performance often exceeds. At this point, flight computers become essential. A modern fighter jet cannot be flown manually in the traditional sense. Fly-by-wire systems replace mechanical linkages with electronic signals. The pilot does not directly move control surfaces. Instead, they express intent, roll, pitch, accelerate, and onboard computers calculate how to safely and efficiently achieve that outcome. These computers constantly evaluate airspeed, angle of attack, structural limits, G-forces, engine state, and aerodynamic stability. Thousands of corrections per second are made to control surfaces, engine output, and sometimes thrust vectoring. Without this continuous digital intervention, the aircraft's inherent instability would cause it to depart controlled flight almost instantly. Sensors further redefine how the aircraft is operated. A fighter jet is not simply an airplane, it is a networked sensing platform. Radar, infrared search and track systems, electronic warfare receivers, and data links generate enormous volumes of information. No human could process this data directly, especially under combat stress. To solve this, onboard systems perform sensor fusion. Data from multiple sources is combined into a single, coherent tactical picture. Instead of raw signals, the pilot sees interpreted information, threats, targets, priorities, and safe maneuvering options. Decision-making is elevated from managing data to managing outcomes. Weapons systems follow the same logic. Missiles, guns, and electronic countermeasures are tightly integrated with sensors and flight controls. Computers calculate firing solutions, predict trajectories, and stabilize the aircraft during weapon release. The pilot authorizes actions, but execution is handled largely by software to ensure accuracy and survivability. This reveals the true nature of a modern fighter jet. It is not a machine that a pilot flies in the traditional sense. It is a highly unstable, software-controlled system that uses aerodynamics at the edge of stall, engines at the edge of material limits, and humans at the edge of physiological endurance. Without computers, it would fall from the sky. Without a pilot, it would lack judgment and intent. A fighter jet works because it integrates physics, digital control, sensors, and human decision-making into a single unified system, capable of operating where ordinary aircraft cannot. That is why the fighter jet remains one of the most advanced machines ever built by humanity.